episode 16 of Prologue is amazing. And I just watched a video on answer set programming. There's this system called C-Lingo uh, or Portasco or something from a university in Europe somewhere, maybe Germany. So, um, what it does is it takes what you would see as Prolog code. And so Prolog has the way it works is it does backtracking. System is depth first search for, you know, solving your problem. And in Prolog you can have kind of quite easily turn it into a breadth first search as well. So now both of these are not like the best way to solve problems, combinatorial optimization problems, right? Like doing searches. So this system, well, the answer set programming, what it does is it takes that and it replaces the search method with some sophisticated search method. And there's been sophisticated search methods, these things called SAT solvers and SMT solvers, right? So SAT solvers basically mean something like satisfiability solvers, right there. And like there's a whole slew of these things, right? So there's SAT solvers, which is basically satisfy, that like is constraint solving over booleans. I think that's what it is. Then there's SMT solvers, which is something related, but it's more like they're all kinds. They're all a kind of solver for theorem proving, right, or logic proving, and then there's constraint programming over various kinds of domains like finite domain constraint programming, and then there's the original stuff like linear programming or mixed integer programming, right? Which that's more common, and since I think it was invented in World War II, and like that's how engineers normally come at it, or most people would first think of it, and then this is another method, right? And this is like it takes Prolog code and searches or in more sophisticated ways. Like I was saying, backtracking is the most basic search method, right? Like depth first search, and then these SAT solvers and others, they use other methods, and I think they use like all kinds of the most sophisticated ways they can do it, right? Like they might do random searches, local searches. It's like they go through different ways and try to figure it out. And the technology behind relational databases also does that. Like the planners of relational databases, they don't just do depth first search through the tables. They kind of there's some sophistication to find the query planners to find the quickest route to finding all the answers. So this is roughly what all this does. Um, and so it's very interesting because it's like it allows you to stay in Prolog and get the benefits of that. Like like a problem with Prolog was always speed, right? So it's like you write your problem, but it might take so long to solve, right? Because it's using the simplest depth first search strategy. With this now, you can still stick to Prolog, right? And the way you usually dealt with it in Prolog was to go in and use all kinds of various tricks, like do put in cuts and things, which takes away from the declarativeness, right? The vision was that you wouldn't have to think about algorithms. You just specify your problem and the answer comes out. If you start having to think about the ordering of the clauses in your Prolog program and cuts and things, then you're basically starting to do procedural programming, right? You're basically writing the algorithm, that you would in a normal language. Now, things like linear programming, mixed integer programming, um, constraint programming, SAT, SMT, all this, and answer set programming is it's like you specify your problem and the solution comes out, right? And so, and these are all kind of there's also a thing called they don't just have to be satisfiers, right? Which means it's like give me an answer that meets all the constraints, or give me all answers that meet the constraints. They're also optimization layered on top. So give me the answers that satisfy the concerns, but also give me the optimal answer, and here's the objective function or set of objective functions, and you know what meets the criteria for the best answer, give me that one. So answer set programming does that too. So it's like, and then what it means is like, let's say I was thinking about, well, if I want to do graph algorithms, let's say I want to find the shortest path or the traveling salesman problem, whatever graph problem, you go to a graph algorithms library, right? And that may be the best way to do it. But you could also do it this way. You could just send it to the solver and it would give you a good result. Maybe it would be as good as the dedicated graph algorithms. Like likely not, but maybe the dedicated graph algorithms underlying are just what this would do. So so basically you don't have to it delivers on the promise of Prolog that you don't have to think about solving your problem. You can just focus on specifying your problem and let the computer figure it out. And so, yeah, this is a great thing to incorporate. If you're a Prolog programmer, it's like, rather than resorting to, optimization tricks of ordering and your clauses and using cuts and thinking carefully through, you can just write your simplest possible way you would write your Prolog program and hand it off to the answer set solver and see if that works, right? So that's a great thing, and it's maybe yeah, like it might solve all the problems, right? And the answer set people say the great thing about answer set programming above what is better than finite domain constraint programming or mixed integer programming or SAT or SMTs, that the language you write it in is higher level, right? So if you're thinking of a problem to solve, let's say in other things like finite domain constraints or mixed integer programming, you first have to convert your problem into the integers that you will need to specify your problems, and then specify the constraints over the integers, and then find the solution, and take the integers and convert them back to what you were thinking about. Well, in answer set programming, you don't have to do all of that. It's just like do it naturally with atoms, symbols that you would do it in Prolog, and hand it over. Like you can stick to the problem domain, not take your problem and convert it into something else that would be good enough for the solver to, that would be appropriate for the solver to take. So is in one vague sense, I think in a sense it's the highest level of these automatic solver systems, right? Now, so maybe there's a great opportunity in this. Maybe it's because I often think about converting problems to optimization problems, and then right, and I almost something like a genetic algorithms, or um, like a gradient descent, like or how all these machine learning algorithms, or how you would solve problems in science generally, in how you solve physics problems often is you turn them into optimization problems, and then the minimal path, which is the optimal path, the energy conservation of energy, and the least integral path of things, that's the optimization problem, right? So maybe this specifying in this solves that too. And you get it, like, and this does it along with constraints, and maybe that makes a difference, and maybe you need the constraints to solve it more efficiently. Maybe if you specify optimization problems without constraints, they take longer. Maybe, I don't know. But yeah, so it's a great and yeah, let's see how it goes. Maybe, any problem I tackle, I can be like, yeah, oh, the Prolog is running slowly, hand it over to answer set programming.